In the tutorial session we will cover some of the linear PDEs, how to solve them, which have physics physical significance. Yeah, and let me begin with the topic. The topic is numerical methods for hyperbolic conservation laws. So it's a ocean in general. So there is theory as well as numerics. So some of your department colleagues are here who are working in analytical techniques. So anyhow, I'll start with this, mostly the basic things. So the first thing is the model equations comes from the gas dynamics, especially the conservation of mass, momentum and energy. The thing is how the particles are interacting when the two gases are in a one chamber. So we would like to derive such kind of a models with interest from the physical motivation of an example. Let us consider a traffic flow, a situation, and you are maybe in the highway, and we are allowing two specific conditions. There is no entry and no exit while you are traveling on a highway in a car, and the car should not overtake. We are imposing these two conditions, and let us say if you pick up this car, the car is entering at one point and it should travel and go at other point in general. So the amount of this car is entering at this point and this exit at this point in general. Now we are trying to say, if we see this kind of a phenomena, now we can consider this some point A, or maybe I can take as A and this some point is B in general. So you can consider this distance is as a real number, so x belongs to R. Now we would like to see the mic is mute. No, that I cannot. It's okay. It's okay. No, it's fine. Okay. So now let us define a function. We are saying this function rho is depending on a space which is a x variable. This is, let us say, x variable, x belongs to R, and at entering at certain point T actually, and moving and up to here. So we would like to see the number of cars available in this x belongs to R, A to B specifically at any time. So this is a density function, rho of x comma t, and for any point. So we are also assuming the another condition, A is less than B. The number of cars in this particular interval A to B at a particular time is given by the corresponding integration. So the total number of cars in this particular interval from A to B is given by this particular density function. Which one? No, yeah, it's already on, right?
I can hear you. We have changed it. It's fine, sir.
Okay. So now yeah, so we would like to see the instantaneous rate of change of this number of cars at a particular time t. So we can start with instantaneous rate of change is nothing but the derivative d by dt of this integral term. And this instantaneous rate of change at any particular time is simply given by the number of cars which are entering at this point and exiting at this point. So which means we are denoting as something as new term, which is the flux, which is the number of cars is entering at this point and exiting at this point. So in general we defined as the influx of cars at this point A minus outflux of cars at point B, okay, 1 second, yeah, outflux of cars at point B, and here we are, okay, we do not have any information how to construct a flux, okay. We are taking the flux is also, okay, dependent on the space as well as the time. So flux Q is a function of x and t. Now, okay, what we are saying, influx at a point, influx of cars at point A, which is nothing but Q is a function, should be evaluated at this point A and certain time t, and okay, outflux of cars at this point B, okay. And if you look at this, okay, this, okay, here the assumption, again we made a strict assumption, is that no entry and no exit, okay, on the highway, okay. So immediately we can say the instantaneous rate of change of number of cars, okay, in a particular domain A to B is nothing but this equation, yeah. Okay, now everything is fine. Yeah. So now we come up with this balance law, okay. The instantaneous rate of change of, okay, number of cars in a particular domain A to B is nothing but, okay, the difference, okay, the between this, okay, influx as well as outflux. So this equation is now can be rewritten under certain assumptions that, okay, if rho is a continuously differentiable function, so we can write down by the Leibniz rule, we can push derivative inside the, okay, integration. So now, okay, the case is we can look into this case, okay, push the integration, and this thing we can write down as a space derivative of this function q, okay. Now this, okay, this integrations, okay, is the left hand side as right hand side are defined for all time t in any domain A to B. So we can simply have this integral equation, and this is, okay, the phenomena when we assume all the conditions holds and A comma B are any arbitrary. So we can simply come up with the, okay, the partial differential equation, okay, which is a, okay, rho by dou t plus dou q by dou x is equals to 0, okay. So here, okay, the conditions, okay, obviously two conditions we are, okay, talking about. The one is no entry and no exit on the highway, and the second thing is, okay, what we assumed, the thing is the cars should not overtake. So if these two are there, then the model equation will change into the some other form in general. So this is the simplest example for the conservation laws, okay, whatever the number of cars are entering at one point, exiting without any change. But in general, okay, if you would like to see a complications in the model PDE, now, okay, it depends on, okay, certain conditions and how the driver is driving the vehicle. Now, okay, can the driver increase its speed? So this depends on the information available, okay, ahead, okay, of his car. So how many number of cars available inside, okay, ahead of his car. Now depending on that, he can, okay, utilize the acceleration, then, okay, increase his speed, obviously, okay. So now we are not going to look into that kind of a perspectives, because, okay, the model equations in that case not going to utilize the local information, because whatever the information within the car is not going to be utilized. So you need some other information which is ahead, okay. This is generally called as a non-local conservation loss, okay. So you are going to use something which is not, okay, incontrollable, okay, in general. And second thing is, this should not overtake. So if they are trying to overtake, so the trajectories will be different from one, okay, car to the another car. So it's a wave propagation phenomena, it's quite difficult to handle, okay. So this again is a complication. So we are starting with a very basic here, and we can, okay, give more, okay, complications into the PDEs, then okay, we can solve. So now still we have one question, how to okay model this flux function Q. So we started with something arbitrary, Q is a function of x comma t, we do not know, so what kind of Q will fit according to the PDE, okay, or physics of the model problems. Now okay, the thing is, it's reasonable to think Q is a function of okay xt as well as the density. The flux is depending on the density function now, okay. And for example, if we take this density function is a linear function, it's a linear function in terms of the only density, okay. C is a Q is flux is nothing but constant times of density, where constant is any arbitrary from the real number system, especially the r plus here. So here okay, why I am taking this one is a positive constant, then I'll okay I'll discuss it later. So this constitute a model equation is a linear advection equation, okay. So why we are calling as advection also I'll tell, okay. This is a specific equation from the gas dynamics, okay. Yeah, and if you are taking this Q, which is a non-linear function now, okay, rho square by 2, the okay the famous okay equation is okay Invised-Burgers equation. If the okay fluid dynamics community is here, then they may call it as a okay Burgers equation, or maybe okay they might be familiar with the viscous-Burgers equation, okay. But anyhow, there is no viscosity involved here. So now the thing is okay, we have this kind of an equation, okay, we have this kind of an equation. How to solve this kind of an equation? So under which conditions we can solve? This is the first question. So again okay, we have okay the other complication here. So we can also include some more okay complication, that exits as well as the entries on the highway, okay. If this is the case, the model equation remains same, but okay we will have some kind of a non-homogeneous term on the right hand side, okay, which will represents for this okay source and sink, or entry or exit for the given okay model equations. So since the equation is remains holds for all okay points in a to b for all time t, then it's constitute the okay non-homogeneous equation. So in general okay the complication is not with respect to the okay PDE, the not only with respect to the flux function, how to choose this, how to handle it, but also with the source term in general. So in general okay the cars may come and hit at some time, okay, this is in the okay basic okay rule on the okay highway. Or if we see the same model equation in the gas dynamics, the particles may interact rapidly, okay. So the particles, if you okay consider any two particles, they may interact very fastly or moderately slow or slow. So if they okay interact rapidly, then this non-homogeneous term may be okay stiff, okay. So it's quite difficult to handle for the scalar equation first, then okay we will see into the okay systems later, okay. So the idea is I'll restrict whole okay lectures in the okay direction of solving the linear advection equation numerically, okay. So before going that, do we have any okay theoretical aspects, okay. So the first thing is, this is a first order PDE, especially the linear PDE, can we solve it, okay. So the thing is okay for example, if you look at this, okay, I'm just changing the notation here. Instead of density, okay, I'm using some u variable, okay, for the sake of convenient, and okay. So now see this A maybe is a function of x and t here, okay, because while the okay driver is driving the car, so this is generally a constant, okay. Constant may depending on the okay physical phenomena of why and how this driver is driving the car, okay. So it is not simply a constant, the velocity. So this velocity depends on the some other external factors, okay, in general. So we can see like that here. So okay, I'm using here is the shorthand notation. So u sub t plus a into u sub x is equals to 0. So derivative with respect to time and derivative with respect to x is equals to 0. This is a linear advection equation with a okay a is a constant, then later I'll try to utilize this as a some external parameters. Now how to solve this equation? Okay, so from the PDE point of view, this is a first order PDE. Now to get a solution, we need to supplement some kind of an initial data, obviously to remove the constant. So we are giving initial data now. Obviously the car has to start at some initial position, so we need some kind of an initial data, right? So at an initial point at t is equals to 0, we have some kind of a function u naught of x, and this may be any function, in general. It may be a continuous function, it may be a differentiable function, it may be a integrable functions, and so on. So the theory is very rich. So depending on the choosing class of functions, the solution structures may change. Now the PDE is supplemented with the initial data. We would like to solve the simplest case is method of characteristics. So this is what you know from the PDE theory. So the whole setup of method of characteristics is convert the PDE, first order PDE, into the first order ODE and solve it. This is what you know from the Lagrange's method, even from the PDE equations. So what we are taking here, we are trying to parameterize the function, because u is a function of x comma t. So if you parameterize it, so because it is going to be looking like a curve, so first thing is we are going to parameterize it. So x is going to be a function of t. Now u of x comma t, if it is a solution structure, so now how I can say, so u of x comma t is a solution. So when I parameterize it, u is a function of x of t comma t. Now what is the case? If this is the solution, then it should satisfy the given PDE. This is the first simplest thing. Now if I parameterize this curve, now what I will say, I am just trying to do derivative with respect to t here, d by dt. And for instance you may forget about this. For instance you may forget about this. So d by dt of u. So now this is a function of two variable, then we can utilize the chain rule now. So dou u by dou t into dt by dt plus dou u by dou x into dx by dt. Now if you see, and this dt will get cancels off, obviously, then you will have the PDE. But the original PDE, if you look at this, the original PDE is ut plus a into ux is equals to 0. Now if I make the derivative is going to be 0 here. So this one as well as the given equation I can see equivalent under certain conditions, that so if du by dt is equals to 0 means u is a constant function, but you have a certain function dx by dt should be equals to a. So u is a constant function along dx by dt is equals to a. Now so u is a constant, so you are giving a initial data which is u naught of x. You are giving an initial data u naught of x, and solution is becoming as constant. Solution is becoming constant along this lines. When we solve dx by dt is equals to a, so we may get some kind of curves that we will talk about it. So you give an initial data, and the initial data is simply propagating as a constant. That's it. I do not know whether it is propagating or not. Now the case is dx by dt is equals to a. Now if this is the ODE, we are converting the PDE into the ODE structure. Now to solve the first order ODE also, we need to supplement one initial data, because we already parameterized the curve, x of t. Now can we parameterize the initial data first of all, then bring up the conditions. So if I have this is the initial data, when I parameterize it, if you look at this, u is a function of x of t comma t. So initial data is at t is equals to 0, so I can start with x of 0 comma 0, which is nothing but u naught of x is a function of t, so t is going to be 0. This is going to be 0. Okay, so this is the first thing, and this is equivalent to u naught of x. So u naught, okay, x is a function of t, x is a function of 0. So x is a function of 0, we can write down something as x initial value, x0. Okay, now when we parameterize it, x of 0 is nothing but x0 and t of 0 is nothing but 0 at time. Now what we have, okay, ODE, right? So dx by dt is nothing but, okay, a is a function of x of t comma t, and okay, here here you have x of 0 is nothing but x naught. Can we solve the ODE? Okay, now is it always possible to solve the ODE? Under which conditions we can solve? Is it always able to solve the given first order ODE? What is the theory saying? We cannot solve, okay, the given first order ODE at all conditions, right? So we have a, okay, existence and uniqueness theorem that, okay, dy by dx is equals to function of x comma y of x naught is equals to y naught, okay, whenever the function of x comma y is continuously differentiable function in a rectangle domain, okay, R, and if it is satisfying the Lipschitz condition, there exists at least one solution. This is only the sufficient condition, not the necessary. Okay, so we cannot solve all the time this, okay, ODE. Okay, so there may be a solution, there may not be a solution. So now instead of taking the a, which is a constant, now you take some complicated function here. So in that case we are unable to get the solution structures. So this is where, okay, the beginning of, okay, existence of the numerical techniques, okay, for solving this kind of PDEs. Okay, so now here how to see, okay, the solution is constant along all the xt domain now. So when we solve this, okay, so let us solve that. Okay, so this is the corresponding ODE in this case. Okay, so it's a, you can say, okay, integral by parts, okay, separation of variables, you can see here. So you can apply integration over dt is dx is equals to integration over, okay, a into dt, then, okay, you will have a curves x of t is equals to a t plus some integration constant z. In order to remove the constant, we have to utilize the initial data here. X of 0 is nothing but x naught. Okay, right? So if we imply the initial data, so you may get constant as the initial point x0. Okay, so now what is this curve? X of t is nothing but at plus x naught. From this, what is the x naught value? I can get x minus at. Okay, but what is the solution structure now? Okay, u is a constant along these lines. Okay, from here, so if I have some solution over here, okay, u is a constant along the, okay, these curves. If I have some solution over here, it is the same over the initial data, right? So it's simply a propagating. Okay, so now here what I can say, u is a function of x comma t, which we already defined as u naught of x naught. X naught, now we already found out that it's a curves x minus at. So the solution u of x comma t is nothing but u naught of x minus at. So where we started with, okay, u naught of, okay, x. Okay, this is the initial data. Okay, this is the initial condition. Now solution is u is equals to u naught of x minus at. Okay, it's propagating. It's propagating from one position to the other position depending on the, okay, sign of a variable a. Either it may be a positive or negative. For instance, we can, okay, talk about the positive. Then it's the simplest case here is that, okay, if you take any kind of a, okay, discontinuous function here, it simply shifts, okay, the data to the, from the left to right in general. Okay, so now, okay, as I said earlier, u naught of x, okay, this may be belongs to any set of class of functions. Okay, so here if I take, okay, discontinuous data, okay, it is propagating from, okay, even the discontinuous data. Okay, that's why it's generally called as a advection equation. Okay, advecting something from one point to the another point. Okay, and from the computational gas dynamics community, okay, for example aerospace engineers, they will call it as a convection equation, or maybe it's from the engineering points of view, this is also called as a convection, advection. Okay, there are so many names for the same PDE, okay, depending on the physics. Now, okay, if I look at this is the initial data, how does the solution look like? Now the solution look like, okay, this x is simply replacing by x minus 8 if you look at this. Okay, remaining structure is same. Okay, u of x comma t is nothing but 1 as well as 0 as it is, but it is changing x minus 80 in the interval 0 to 1. Now the initial position is starting with 0 and 1. Now the new positions are 80 and 80 plus 1. Okay, now the case is, this is for the linear PDE. Okay, we are considering A is simply a constant. Now let us consider a situation A is, okay, the constant is depending on the solution structure itself. A is a function of something, okay, u of x comma t. So you may consider some external factors obviously, or internal factors, okay, while driver is driving the car, simply. Okay, now, okay, if I have the same situation, so what is my solution? It should advect the same thing in general. Okay, I already solved PDE with some initial data. If I change a small thing in the PDE, so I should expect the same kind of a behavior, or should I expect something more? Yeah, this is the question. Yeah, this is the question. So now when it comes to that, okay, if A is depending on you, okay, so A still is a constant, but A can be determined based on the some external factors, okay, of the flow, okay, or gas dynamics. Now if this is the case, I have to solve new ODE. Dx by dt is equals to A is a function of u, and then x of 0 is nothing but x naught. Okay, now I can solve it, okay, obviously, okay, the solution, the curves, okay, these curves are called as a characteristic curves because it's giving the characteristics of the given solution structure, okay, of the PDE. Okay, so now x minus, okay, A is a function of u of x comma t and t. Okay, and okay, obviously it is supplementing with the initial data now. Okay, so what is the solution? The solution is this. Okay, u of x comma t is nothing but u naught of x naught. From this, okay, we already solved what is the x naught, okay, by solving the ODE and replace the x naught in terms of x and t. Okay, if I do this, okay, can I get a solution first of all? Okay, so can I get a solution for all the time t? Okay, in the initial case, it is advecting from one point to the another point. There is no restriction on the these characteristic curves and so on. And when you take the derivatives and substitute back, then you can consider as a regular solution or smooth solution. Okay, yeah, then it depends on the classical solution or weak solutions that you can consider. Now here, if I start with this, if this is my solution, and in principle if I take the derivative with respect to space as well as the time and go back and substitute into the PDE, it should satisfy. Okay, I have some simple function. Okay, so now what is a function? Okay, I can differentiate with respect to t. Okay, if I do differentiate with respect to t, this is a u naught of x naught. So in general this is like a something sine of theta. Okay, theta is some function of other. Okay, so u naught dash of x naught into x naught is differentiate with respect to t. Okay, again ux, this is a u naught dash of x naught into x naught with respect to x. But what is a x naught? This is my x naught. Okay, I need to compute dx by dx naught by dt and dx naught by dx. Okay, so if I have x naught, and the first step we are doing is dx naught by dt. Okay, again this is the case, you can see. So this is a x variable, there is no role of x naught, so it's a simply 0. And now this is going to be uv rule. Okay, it's a chain rule again. So a naught dash into u naught dash, then again x naught should with respect to t, and t is as it is. And in the second part, you will differentiate with respect to t. It will be 1, So this is the corresponding equation. Now if you see, x naught sits in the left hand side as well as the right hand side, bring together and push the remaining term into the denominator. This is corresponding x naught sub t, differentiation of x naught with respect to t. And similarly you can compute x naught with respect to x, differentiation. So again, when you do x naught with respect to x, this is going to be 1, right? And this is again going to be with respect to x, so a dash, then u naught dash, then dx naught by dx times t. Again x naught x sits on the left hand side as well as the right hand side, then bring together and push back. Now you have two variables, one is x naught, x naught, x naught t as well as x naught x. We computed from here, then go back and substitute here, then compute, what is this, ut plus, a is a function of u into ux. Is it going to be 0 or not? This is, if it is a solution, it should satisfy the equation, right? Now everything is computed. Now let me substitute everything. It's a detailed thing I have written here, ut and u naught, ux. Now can see when you substitute it, it is satisfying the PD obviously. But here there are conditions we are bringing something new into the equation. So when we are doing the differentiation here, if you see, this is the derivative exists for the a. A is a now sits in the C1 class of functions, and u naught, u naught is also derivative exists, so it's a C1 class of functions. Now a and u naught, both are in the C1 class of functions, but our initial assumption is not. We started with the u naught is a any class of function, but PD is pushing us in order to make it as a solution, u naught is a C1 function. So what's happening, now it is the case, if you look at this equation, so as long as if you see a dash as well as u naught dash containing the same sign, let us say both are plus, both are minus, so this product is going to be both the plus. So 1 plus something is never going to be equals to 0, so we do not have any issue. But one of them, let us say this is a positive, this is a negative, this product is going to be negative because t is always a positive value, time value, starts from 0, so it's always positive. This is a positive value but multiplied by the negative term, so 1 minus some term of t. So here you can see 1 minus some term of t, this may goes to 0, right? So t is going to be this towards to the 1 by something, 1 by this term. If this is the case, we may encounter a situation that this is going to be 0, then the solution is not well defined. If the denominator is going to be 0, obviously, so solution will blow up. So we are bringing some other conditions now. So one can solve such a phenomena up to certain time. For all time we cannot solve. Whenever it depends on the chosen initial data now and chosen condition on the a. So in principle, what we can say, we can solve this PD up to certain time level for not all time t. So in general, now the question raises that this time is generally called as a threshold time, or maybe it's a critical time. So what's happening when the solution structure is going to be blow up? What is really happening? So I would like to give a simple example here. So if you start with the it's fully nonlinear PD, let us say this Burgers equation, even with the smooth initial data, sin 2 pi x is a smooth initial data. Now if I apply this, so now I'm trying to make this, let us say if you write down this equation into the okay, non-conservative form, okay, this we will talk about later, okay, ut plus u into ux is equals to 0. So you can do the derivative and okay, you can get this under the okay flux is smooth, q is okay, this flux is C1 function. Okay, now what is happening in general, okay, here? So if you see, okay, the solution structure is going to blow up. Okay, initially, okay, let us say this is your initial data sin 2 pi x, let us say, okay, within a certain domain 0 to 1, let us say, and you can solve the solution up to certain time. This time is okay threshold time or critical time. Okay, we are defining as t sub t c. Okay, after this, okay, the solution is going to be blow up, or okay, we cannot trace for any given point of x and t. You may encounter a single u. So you may have multiple u's for a given x comma t. Now this is the now for t is greater than t naught, the okay the curve keep on bending maybe. Okay, so for example, if you would like to compute the solution over here, one solution exists over here and one solution exists over here and one solution exists over here. So for one value you may encounter 3 solutions. So single value solutions becoming multi-value solutions now. Okay, this is the phenomena where you can see say okay, solution is becoming to be multi-valueness. So to remove the multi-valueness, what we can do, a simple thing is, okay, the nice idea is, okay, so how do I remove? Okay, if I need to see the solution over here which is the same as the solution over here, yeah, oh okay, yeah, sorry, yeah, so what, no I'm seeing, I don't know why, no, yeah, one second, it's coming. Okay, anyhow, okay, I'll, so to remove the okay multi-valueness here, okay, so what we will see, you can inject okay a one value instead of multi-values. Okay, so here instead of to remove the multi-valueness, you can inject okay single value. Now this is you are replacing by a continuous solution to be a discontinuous point. Okay, now initially the curve is okay, you can see this curve is okay a smooth curve, you are injecting okay, this is by okay a discontinuity. Okay, so this kind of okay, so now here whatever the information you are losing here, okay, you have to lose the same information over here in order to inject the right discontinuity. You cannot okay inject the random okay discontinuity in order to preserve the physical okay significance of the given PDEs. So it's not random in general, so you have to carefully inject some okay discontinuity. This kind of a solution structures is generally called as a shock solutions. So you can see the solution okay, you are starting with the initial okay, it's a smooth solution. As okay time is propagating, okay, you may encounter a discontinuity now. Okay, now okay, this kind of solutions where we can okay define, okay, this is the question. Okay, so now the whole okay structure we can see in the terms of okay weak solutions, okay, which is okay is a classical theory of okay distributions and weak solutions, how to define that. The simplest case is here, okay, if you see u is discontinuous in x for example, okay, then a is depending on u, this is also a discontinuous in x, then the derivative of u we can simply call as the Dirac mass in general. Okay, so now the case is we are looking at the product of okay this a is a depending on u and then derivative. Okay, this is not well defined in a classical way, so we have to define some new way. The some new way is nothing but the okay the theory of distributions and weak solutions. Okay, anyhow I'm not going to discuss much on this. Simplest thing, okay, you can see what is this ux is become as a Dirac mass. I hope so. Okay, everyone, maybe it's a 90s kids okay here, yeah, at least okay, or before that, maybe if you try to watch maybe black and white TV, for example, if suddenly power off, then you might have encountered to see a small bubble at center of the TV. So what's happening here? Say whole energy is encountered at single point, right? So now so U is discontinuous, let us say, but derivative is is a Dirac mass. It's entire energy is located at one particular point. A simplest thing, when you if you are experienced watching black and white TV, I do not know how many of you, anyhow, yeah. So that's what the Dirac mass actually, so entire mass is located at one point in general. So now this is the theoretical portion now. So we would like to see more ways how to solve this equation. So this is maybe it's encountered in 1950s and before, maybe weak solutions are started from 1950s in general. So the author who produced it got the this Fields medal. It's first one, yeah, obviously. So I'm not discussing that further. So I would like to discuss here how to solve this linear advection equation numerically. So in early days in 1950s, so maybe it's one I'm understood in a good way that how to solve these PDEs and other scientists or mathematicians. So now I would like to start doing simple technique, which is the finite difference technique. This is so called theory. Theory is suggesting that you may encounter discontinuities. Discontinuities you may not able to solve by the classical way. That parallelly, let us say the numerical techniques. So a simple thing is finite difference techniques. So we will take the PDE. We do not have any kind of external conditions, let us say. So we are taking the same domain, as well as the range of the functions here, whatever the precise thing, initial data and boundary data and so on, in order to solve. So first order PDE is supplemented with x belongs to R and t is from R plus always, and u naught you can take x, the u naught of x belongs to R. But in general, if we give this PDE, so if we discretize by the finite difference techniques, are we really able to solve this PDE in a computer for all time t, for all time x? So x belongs to R we cannot store in the computer. So every computer comes up with some memory, which is the finite, right? So obviously x belongs to R we cannot solve. Now we have to discretize or truncate the domain first. Let us make it the x belongs to R to the some simplest case that we are bringing into the XL to XR is a closed domain. This is the first thing, because every computer comes up with the it's limited memory. So now that's what the case. Now if you are doing that, if you are truncating the domain, so x, let us say x naught is nothing but XL, xn is nothing but I don't know why this is not coming. X naught is nothing but x left value, and this is a x right value. This is for x, as well as t. T belongs to R plus again. We can start from t is equals to 0. Maybe t is maximum value, maybe let us say capital T. So t also domain is 0 to t. Now we can discretize the space variable, we can discretize the time variable now. So first we have to define the mesh. What is the mesh here? XL to XR. So we are defining the mesh with the here equidistance, because distance between any 2 points, you can start with a very simplest case. Distance between any 2 points is a constant. If it is not constant, then you will end up with the non-uniform mesh. So xj is nothing but xl plus j into delta x. So j is running from 0 to n, and delta x from this you can compute as a fixed constant. Distance between any 2 points. And similarly for the time, time is again tn, we are using the notation tn is n into delta t. So you can find the delta t also t by capital M, the number of mesh points, t minus t naught, which is nothing but t minus 0 by how many number of discretization points you are utilizing it in order to get it. Now, so u is a function of x comma t is your solution structure, but you are bringing the continuous maybe it's an infinite dimensional solution into the finite dimension, because you discretized it already. So you need a map actually. So the original PDE solution is in the terms of x x comma t belongs to r comma r plus. Now we are discretizing it, and truncating it and discretizing it. So there should be a map to the finite dimensional space to a infinite dimensional space, right, in general. This is the first case. So unj we are defining as so solution at some point xj and tn, and xj you can write down as j into delta x, and tn we can write down as a n into delta t. So first thing is we need a infinite this finite dimensional map to the infinite dimensional map. This transformation is required. Otherwise what we are solving, we are solving on the finite dimensional domain. Whatever the solution is there, it may not be equivalent to a infinite dimensional space solution structure. So we need to make some kind of a limit map. That is we will see. So now let us evaluate the derivatives with respect to differences, the finite differences now. So how many ways we can do? I'm only giving here. In total you can see all the ways are 16 ways to do that with different kind of structures, but here I'm only seeing here this is always forward in sense. You can also consider as a backward. I'm not considering that, but and now how to discretize this by the finite differences. Obviously you can use forward derivative, backward derivative, maybe central derivatives, 3 of them. Let us go with these 3, then we will analyze solutions. So now first case is forward in time and forward in space. Now if I do that, forward in time, this is the how do you see u of xj comma tn plus 1 minus u of xj comma tn upon delta t, which is a finite difference approximation of the first order time derivative. And this is the finite difference approximation of the first order space derivative, and it will come up with a some higher order terms. This higher order terms is defined as a tau here. This we can generally call as a truncation error. So in principle we already said that so this has certain role here in general in order to map finite difference solution to the infinite dimensional solution structure. That we will see. So tau jn you can see, so this is considered as a big O of delta x and delta t. So order of delta x and delta t, this higher order terms and truncation errors. So now for instance you may drop this truncation error and understand the solution structure then. Let us so dropping the truncation error, so now the PDE PDE is going to be a discretized algebraic equation now. So now you can see un plus 1j is nothing but unj minus this term a into delta t by delta x of space derivative difference. This is now, for example, if you see the thing is if we have n level solution, we can find the next level solution. In precisely if we have initial data at 0th level solution, we can find the first level solution, but are we going to get it actually? That is the question. We discretize the PDE very nicely here. And if we do program, then can we do have solution whatever is expected. So now the case is you can see this you can do in principle. This is the your I don't know. This is not good. So in principle this is the this equation which you are going to solve in a by programming. Now here you can write down the equation like this: 1 plus lambda into unj minus lambda into unj plus 1, and j is running from 0 to n minus 1, and n level is running from 0 to m minus 1. For example, if I need a solution at n value, j is nothing but n value. Okay, so I need this one is n plus 1 value, but discretized domain doesn't contain the n plus 1 value. We discretized from space is from 0 to n, time is from 0 to m. Okay, so you cannot take the value at most right this part. Okay, so you can calculate up to the previous point, up to this previous point. So to compute and execute the solution, you need this data at the end. This is generally called as a boundary conditions. What kind of a boundary conditions one has to impose in order to get solution structure. So far we discussed only the initial value problem. When we discretized it, now the boundary conditions are encountered. So depending on the physics or physical situations, we will take different kind of boundary conditions, either maybe a periodic or reflective boundary conditions, maybe because of this is the wave propagation phenomena. So the wave may go and hit at some wall and come back. Maybe water, it's a fluid, may go and come back when it hits the boundary. Now this is one of the numerical scheme: forward time and forward space. Now we can also replace space derivative by the backward space, right? So we can also do by the backward space. Same thing. Now when you are doing by the backward space, so discretized point starting from 1 to n, but it is at 0th position you may not have, so you need the value at 0th position. Now this is again we have to define the boundary rate here. Now then forward time and center space, when you give the second order derivative term for the space derivative, now you need both the things, 2 delta x. So j is running from 1 to n minus 1, n is running from 0 to m minus 1. So in this case you do not have leftmost point value as well as rightmost point value, so you need to give both the conditions. So we will execute these codes in the afternoon tutorial session, and we will see whether really the linear advection equation can be solved by the forward time forward space, forward time backward space, and forward time center space. So then what are the difficulties we will encounter? So that we will see in the afternoon. So the first thing is we need a map, right? Finite dimensional space to the infinite dimensional space. So this is generally called as a consistency of a given PDE. So discretized PDE should approach the solution of the discretized PDE, or maybe I can say it's as simply as discretized PDE should be a approach to the continuous PDE only. Under truncation error pushes to 0. So truncation error is depending on both the discretized parameters, delta t as well as delta x. So as you are pushing the delta t and delta x goes to 0, tau should goes to 0. This is a consistency. I'm not talking about anything solution structure here. So when this discretized solution structure is going to continuous solution structure, this is now a convergence. This is consistency of the PDE. Consistency and now convergence. Now we will talk about something accuracy also. So now one can start with here forward time forward space. This is the first order in space and first order in time. Now you can also talk about forward time center space, first order in time, and second order in space, right? So you can define accuracy of a numerical scheme. So here the numerical scheme is accurate of order p in time and order q in space for sufficiently regular solution of the exact solution. If the truncation error goes with big O of delta t power p plus delta t power q, delta x power q. Okay, so for example, if you see forward time, forward space, delta t is 1 and okay, delta x is 1. Forward time, backward space, delta t is 1, delta x is 1. Forward time, center space, you can see, okay, delta t 1 and delta x power 2. Okay, this is the order of accuracy. Now, okay, we are bringing something, okay, okay, here this CFL condition, which is okay, Courant-Frederick-Levy condition. This is okay, responsible for stability of the given PDE that we will talk about, okay, in the next lecture maybe, or in the afternoon more precisely when this is posted. Okay, I think I have enough time. Maybe I'll come back and okay, in this CFL condition, what is that and what is the significance of that. Okay, okay, this is all about the numerics. Now, okay, numerics we can evaluate in the afternoon session. Okay, we'll come back to know that one of the scheme is going to work out of 3. Okay, why the other 2 are not going to work out. Okay, so I would like to give the reason. Okay, we will see later in the afternoon. Okay, so now if you see forward time and forward space here, okay, I just need this thing, forward time and forward space. Okay, now, okay, if you discretize, okay, this is the j plus 1 and j minus 1. This is a tn level, tn minus 1 level and tn plus 1 level. Okay, discretized PDE. Okay, so now what is the okay thing? So this is the forward time, forward space. Okay, so let us say we are discretizing ut plus a into ux is equals to 0, maybe with some initial data, not okay, this is important, and let us impose a condition a is positive. Okay, so what is the solution? Okay, solution we know from okay, theoretical x, okay, thing, x minus 8, u naught of x minus 8, whatever the initial data is propagating from left to right. Okay, now if you look at this, okay, I am going to execute a solution at un plus 1j. This is what I need over here. Okay, from the okay numerical scheme, what I have one point here unj. Okay, the other point is unj plus 1, right? Okay, but initially what I need, okay, solution is propagating from left to right. Okay, but what is the numerical scheme is feeding? Okay, I have a point here and I have point here, it is giving from the right side. Your original PDE solution structure is giving from left to right as time is propagating. But okay, here the discretized okay PDE okay is giving from right to left value. Okay, so the data, okay, whatever the characteristic curves, okay, x minus 8 is equals to some constant values. Okay, if it will be like okay these green lines, okay, the characteristic curves on the some kind of a slopes. Okay, here when you trace it, okay, it's xt plane, then you can write down x minus 8 is equals to constant. It's a simple okay, y is equal to mx plus c kind of a curves, then you can trace it. Now the curves are okay moving from left to right, but numerical solution okay is giving the data from the right to left, which is something wrong in general. So that's why the forward time and forward space is not going to work out. So this is one thing, and second thing is okay, this is okay. So now if I replace forward time forward space by the forward time backward space, what is the backward space? Okay, so the scheme is as it is, okay, except here what you will have unj minus unj minus 1, right? So you will have a solution okay dependent on this value and this value, and you are going to compute this value which is aligned with respect to given original PDE structure. Okay, so the numerical domain where you are solving is important when it is aligned with the physical domain of the given PDE. So you cannot discretize the numerical solution at somewhere else and physical PDE discretization at some other place. This should both overlap, otherwise you will not get the solution, right? So now here okay, if you look at this value is delta x, this value is delta t. Okay, so now if you look at this is exactly delta, okay, t by delta x is the slope. Okay, so delta t by delta x is a slope here. Okay, this is the numerical domain, okay, slope. But you have a is defining as, okay, slope value. Okay, so physical domain and numerical domain both should coincide, okay, which means that the ratio should be maintained within a given discretized cell. Okay, so now this within this cell, okay, so this is the discretized domain, so I can talk about, I don't know whether, okay, a may be this value, 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 anything, but okay, delta t by delta x is fixed. Okay, so this ratio a into delta t by delta x we can write down as, okay, the ratio between the, okay, physical speed to the numerical speed, delta t by delta x. If this is controlled, by some kind of a condition, that is called as a Coran-Frederick-Levy condition. Why this is needed, that we will see. Okay, less than or equal to 1. Okay, is that clear? Okay, good. So forward time, backward space. Okay, so similarly forward time, center space, you will have, okay, the same structure. Then, okay, you need some kind of a condition here, Coran-Frederick-Levy condition. Okay, that why this is the case we will see in the numerical, okay, the evening class. So this is about the theoretical stuff. Let us look at this. Okay, so we do have one more thing. So these equations are also considered as a energy equation. So can we calculate the energy, actually energy functionals or energies of a given PDEs, okay, a priori as well as a posteriori. So I have a PDE, okay, so I would like to solve this PDE solution. So can we get some kind of information before solving it? This is generally called as a priori estimates of the given PDE. Okay, so now this is okay, ODE and energy. Okay, so if you look at this, energy is nothing but kinetic energy plus potential energy. So potential energy we are ignoring, obviously. So kinetic energy is a bigger thing. So u squared by 2 is a something, okay, you might learn in your, okay, plus 2 or maybe physics, okay, BSc. So okay, v square by 2 is a term which is, okay, called as a kinetic energy. So here we are defining with respect to the solution structure, which is a u square by 2 in a over the all domain integral over R. Okay, so okay, I'll come back to this lemma. Okay, so how do we calculate it? Okay, so the case is, this is the linear advection equation. Okay, so linear advection equation is, okay, not having any u square term. Now let us bring the u square term somehow. Okay, so multiply by u on both sides. Okay, so I am assuming, okay, all the conditions whatever is necessary here, there are no, okay, specific conditions, so that I'll tell you later. So the first case is, okay, multiply by u on both sides. Okay, so now this term you can write down as a u square by 2 under, okay, whenever this energy function u square by 2 is a C1 function at least. Okay, and a is a function of, okay, this u into ux can be written as u square by 2, okay, with x. Okay, now we are adding and subtracting this term, okay, this term as well as this term, adding and subtracting, so there is no change in it. Okay, now the case is, okay, okay, so here you can write down these two terms as this term. It's a differentiation of, okay, a and u square by 2. It's like a UV rule. Okay, and you will have this term on the right hand side. Okay, now so everywhere if you see, it's a u square by 2 term is coming into the picture. Now can I integrate with respect to R? Okay, let us do that. Okay, if I integrated this and integration and integration. Okay, now again I'm using, okay, is a smooth function, so you can push t to the outside by the Leibniz rule. So you will have d by dt integration over R u square by 2 into dx, and this is r and this is with respect to space, so integrations, okay, will get cancels off, okay. So you'll have a of x comma t, okay, into u square by 2. You have to evaluate at the boundary of the r. R is maybe minus infinity to plus infinity, and this is the, okay, as it is term integration over ax, okay, u square by 2, okay. Now r is really big, okay. So let us start with this, okay, thing. Either it's maybe a periodic boundary conditions may be encountered with the physics of the model problem, or zero boundary conditions, let us say, okay, which means that as mod x goes to infinity, either x is goes to infinity minus x is goes to infinity, if the solution is going to be 0, okay, so you can write down this term immediately to be 0 because u is going to be 0. Now what you will end up with, okay, this term as it is, this term as it is, okay. Now what you will see, okay, so we have something from the ODE theory, Grunwald's inequality. What is the Grunwald's inequality? Okay, if any function is continuous, okay, b of t, okay, and u of t is also a differentiable function in an interval, if this is my ODE structure, u dash is bounded by, okay, b times of u, then u can be written as in the terms. This is the Grunwald's inequality, okay. So I am going to utilize the same thing here, okay. This is d by dt of this term, this is a u, okay, this is a u, okay, this is now b, okay, it's a beta here used. So if I use the Grunwald inequality, so u squared by 2, which is a ut, and bounded by, okay, integration over r, so u of t is as it is, so this is a u of a. So at the initial value it should be evaluated, so u square by 2 at the initial point x comma 0 to dx, and exponential function, okay, since it is a t is defined 0 to a to b, in our case it is a 0 to some t, so 0 to t, and beta of t is nothing but, okay, norm of a under c1 function, okay, norm of a under c1 function into dt, okay. So what is the case, okay, if you see now, okay, this integration with respect to t and t will get cancels off, then it will be a exponential term, okay, and this is, okay, initial data. So now what is it is saying, okay, under these conditions, so now a is a c1 function, this is first case, and under the periodic boundary or zero boundary, okay, so the solution, the energy at any time level should not be, okay, go beyond the initial data with some constant, but I do not know what is this constant, so it depending on the structure. Before solving the PDE, here it is telling us that energy, okay, is going to decrease, okay, when it starts from the 0th level to the nth level. But okay, if this exponential term is really big, so obviously we cannot, okay, bound it, so we cannot get a solution. So it depends on the exponential term as well as a is a c1 function. So now, okay, the case is, so why this energy has to be decreased from one level to the another level? This is another question for us, okay. So energy is conserved, okay. So if, okay, any PDE comes from the model equations, so so energy at, okay, initial level should be a bigger, and when it, okay, going time from one level to the another level, it should keep on, okay, the same or maybe decrease in the manner, so that you can control the PDE and you can solve it, you can control the solution of the PDE. So now this is what it is, okay, telling us, okay, before solving the PDE, but here we, okay, have seen so many, okay, conditions, we multiplied by u, and we have taken some zero or boundary conditions and some conditions on a. In the conservation laws, okay, you cannot change the PDE, you cannot multiply by the PDE to the, okay, some other term, because if the moment you do that, the original PDE structure, the physical structure will change, so you are not going to solve the original PDE. Okay, so here in this case, the first case, if you see, the solving the, okay, this equation, solving this equation and solving this equation by any numerical method is not same. So you cannot add, you cannot delete the data from the conservation point of view. That's what the meaning of conservation, right? Isn't it? So the case is, okay, this is under certain conditions we can estimate, okay, the energy, but does it really holds in a similar lines for the numerical, okay, schemes also. Okay, so now if I start with forward time and center space, can we say this is the energy energy of this solution structure for this numerical scheme is, okay, controllable. Now I can do the same structure, okay, same thing, okay, in the discrete sense also. Okay, so this is my forward time and center space, okay, numerical scheme, multiply by u, okay, instead of u we are doing in the discrete sense u and j. Okay, so multiply it on both sides, this is the multiplication. Okay, now we have something from the, okay, identities, x into y minus x we can write down as y square by 2 minus x square by 2 minus y minus x whole square by 2. Okay, so I can utilize, okay, here, okay, x into y minus x, this is x, this is y, this is x. Okay, so if I do that, okay, the idea is bring the terms into the u square by 2 term, that's what the idea, okay, somehow. Okay, so u square by 2 and this is a term and this is going to be y minus x whole square by 2 and the right hand side is as it is. Okay, now multiply by delta x. Okay, if you multiply by delta x, okay, so what is the energy equation? Integral over u square by 2 into dx. When you discretize it, what you will get? Summation over u square by 2. It's some delta x, right? It's a Riemann sum kind of thing, you can see. Okay, so delta x by 2 summation, okay, multiply by delta x and make a summation over all the discretized values, okay, z, okay, I belongs to z because you have to evaluate at each and every grid node. Okay, so I belongs to z, it's minus, okay, maybe 100 to plus 100, let us say. Okay, so when you do that, the left hand side is not much change, but right hand side you can write down this equation cleverly that, okay, unj and un plus 1j, okay, and okay, as this is, okay, a by 2 I am pushing inside, okay, a by 2 I am pushing inside, a by 2 into unj and unj plus 1 as something hj plus of, and a by 2 into unj and unj minus 1 as hj minus 1. If you replace j by j minus 1, okay, the next term will appear. Okay, so now right hand side term you can write down this way, hj plus of minus hj minus 1. Now when you sum it up over all j, okay, so when you sum it up over all j, so you can see j is replacing by j minus 1, okay, right? So one term is, okay, positive, one term is negative, one term is positive, one term is negative, and so on. This is like a telescoping sum, okay, here, and okay, except the first value and last value, all other values will vanish, okay, right? Minus term and plus term, minus term and plus term, and so on. So first term as well as last term. In order to make it is completely zero, okay, let us say you need to apply some kind of a boundary conditions as we did in a theoretical way. Okay, either it may be a zero boundary conditions or periodic boundary conditions imply it, then you will get the first term is equals to the last term, one is positive, one is negative, it will vanish. Okay, so the whole thing is you will end up with, okay, this right hand side term is going to be 0, so you will end up with this equation. So what is this saying? Okay, this is at energy at n plus 1 level, okay, this is at energy at n level, and this is some other mu term. Okay, so energy at n plus 1 level is nothing but energy at nth level plus some term. So if you are starting with the 0th position, okay, okay, E0, okay, plus some term is nothing but E1. So energy is located at initial level, or okay, first level is can be treated as energy at 0th level plus something. So at each level it's keep on adding the energy. So when energy is really increasing, we cannot control. So forward time center space is not going to be work out for the linear advection equation. This is one of the reason, okay, we cannot, okay, control the energy here. Okay, so the similarly you can do for forward time backward space and forward time, okay, forward space under the condition A is positive and A is negative. Some of them may be, okay, because if the PD is aligned with the discretized PD in a physical sense, then you may encounter that, okay, energy is conserved, so energy is controllable, so that you can say this scheme will work. Okay, so now, okay, this is something called, okay, upwind scheme. Okay, so so forward time backward space and forward time forward space, we do have two things. Okay, one is A is positive, okay, forward time backward space will work for A is positive when, okay, PDE, okay, solution structure is from, okay, is like left to right, then, okay, forward time backward space will work, and right to left forward time forward space will work. Now can we combine both of them, okay, and give any sign of A? Okay, this scheme is generally called as a upwind scheme. Okay, so now, okay, what is the case? Okay, let us combine both the schemes in the space. Okay, time is as it is, we are combining. Okay, so here A is positive here and A is negative here. Okay, this is forward time backward space and forward time forward space. Okay, so I am bringing this as a positive sign because of the backward space and negative sign is because of the forward. So now I can define something, okay, from the identity is that A plus we can define as maximum of A comma 0. So maximum of A comma 0 means, okay, if you give any A value, okay, you can see either it should take as a A or 0. Okay, let us say if it is taking A, so this term is going to be off in general. Okay, then in that case it's a forward time backward space. So if you take the minimum of A comma 0, okay, if A is always, okay, positive, then it is going to be 0, then forward time, okay, forward space will work. So now you can see, okay, we can define this as a 1 by 2 into A plus mod A and 1 by 2 into A minus A, okay, mod A. So mod you can write down as A plus minus A minus. So maximum of A comma 0 minus minimum of A comma 0. Now if I take this is my, okay, PDE, or sorry, numerical scheme. Okay, this should work for any A belongs to R. Okay, depending on the sign, okay, you have to feed this A plus and A minus. So you no need to worry about the, okay, whether A is positive or negative. Okay, so you are combining the both physical, okay, significance into a one numerical scheme, okay, and trying to get the solution structure. But if this is the case, okay, is the energy conserved here? This is the question for us, right? So now you can see A plus we can replace by 1 by 2 into A plus mod A, and A minus is 1 by 2 into A minus mod A. Now you collect all the terms of A together and mod A together here, okay, again. So now, okay, you can see, okay, this is okay, as it is time derivative. Now when you take A together, this is a negative term, this is a positive term, will get cancels off, and mod A by 2, this is the case. Okay, so if you see, okay, this is the discretized, okay, this is nothing but, you can see UT, it's a discretized, discretization, and this is A into, what is this, central derivative, right, A into ux, but it's a central derivative for the first order derivative, and this is modulus of A, right, okay, by 2, okay, I can say 2 is outside, so you can write down as a, okay, this is a, I can write down delta x into uxx. Okay, so now if you look at this, okay, PDE, now PDE is now, okay, you started with ut plus A into ux is equals to 0, A is belongs to R. Now the PD is turning to be ut plus A into ux is equals to some constant, okay, some constant times of uxx. Some constant here is mod A by 2 into delta x. So what is it saying actually? So we are adding the diffusion. Uxx is a diffusion term. Okay, heat equation, right? Heat conduction equation. What is the heat conduction equation? Ut is equals to some k into uxx. So that's a diffusion. So the solution structure is a exponential decay right? Isn't it? Yes or no? Yeah. So now you are adding some kind of a diffusion. This diffusion is generally called as a numerical diffusion. So we are adding numerically. There is no physical diffusion in a original PDE, okay? But to encounter, okay, or to make the scheme is, okay, stable here, and it should work for any A, we are adding numerical diffusion. Okay. So if this is the case, do we have, okay, energy estimate? This is the question. En plus 1 is bounded by En or not? N plus 1th level, okay, energy is bounded by nth level energy or not? Do the similar procedure for the, okay, numerical scheme. Take the numerical scheme, okay, multiplied by UNJ, okay, and use the identities and everything, okay. Under certain conditions, it should be, okay, bounded. The energy is bounded, okay. Let us do that, okay. So again, I'm doing the same thing here, okay, starting with the, okay, affine scheme, okay, multiply by UNJ, okay, and use the identities, okay, this identity again, okay, x into y minus x, okay, I'm adding the identities, okay, the same thing, and multiply by delta x and sum it up, okay. Okay, when you do multiply by sum it, you have to do some clever, okay, computation here, okay, something hj plus of or hj minus of or kj plus of or kj minus of, whichever the terms are going to be vanish according to the boundary conditions. Now when you sum it up over all j, okay, obviously you will see, okay, En plus 1 is nothing but En with some other terms, okay. Again, when you are using the, okay, PDE structures and everything here, okay, now you will encounter entire, okay, situation that this is the, okay, final expression of the, okay, solution structure. En plus 1 is equals to En plus this term into this term. Now this term, okay, is keep on adding. For example, if this is the initial data and you, okay, if you would like to encounter the solution at next level, so it is adding this information at each time level. But can we able to control it? Okay, obviously if you see the parameter is there, right? The parameter is there. Can we control the parameter? The coefficient. So I can say, okay, I can say this En plus 1 is bounded by En, providing that this quantity, okay, is less than or equal to 0. Okay, sorry, less than or equal to 1, sorry, here this is going to be, this is the case. So from this you will encounter the condition that A into delta t by delta x is bounded by 1. If this is the case, okay, your energy for the affine scheme is, okay, bounded. Okay, solution is bounded, okay, energy of the solution is bounded, providing that A into delta t by delta x is bounded by 1. So similar, okay, structure you can work out it, okay, I can share the, okay, notes, okay, you can see it, okay. So if you have any doubts, you can, okay, talk to me, that's fine, okay. It's a similar analysis. So multiply by u, okay, then use some kind of an identities to make the, okay, numerical scheme to look like u square by 2 form. Then, okay, okay, multiply by delta x and sum it up over all j belongs to z. Then you will end up with every numerical scheme in the, okay, for the finite difference techniques to solve linear advection equation. You can apply every scheme and see if the energy is controllable under certain parameters. Obviously your numerical scheme is going to work out, otherwise it is not. Then you can study, okay, all other properties, okay, kind of convergence properties, stability properties, and, okay, why this is working for, okay, one particular initial data, so other particular initial data, or so on. Okay, this is what we required actually. It's a generalization, okay. So yeah, this is the affine scheme actually. This is, okay, invented later. It's 1959, okay. Okay, this is the first, okay, numerical scheme, affine scheme for solving linear advection equation, and generalization is a Godunov method. I think Professor Gowda, okay, will teach that, okay. Before that we do have another, okay, scheme in 1954, okay. This is Lax-Friedrichs scheme, Okay, the authors come up with a nice idea. Okay, what is that? Forward time center space is not going to work. Just now we have seen that. Okay, what they have done, a very clever idea here. Okay, they have not done much. Okay, so if you take this forward time and center space, and okay, you can rewrite down the scheme like this. Keep the n plus 1 term to the left hand side, and okay, remaining terms on the right hand side. Okay, now okay, so this term, if I take the average, okay, so what is my space derivatives? Uj plus 1 and uj minus 1. Now if I take the average of the solution at j plus 1 and j minus 1 level, okay, this scheme, okay, is controllable. The energy is controllable for this scheme. Okay, so this is okay proposed in 1954 by Lax and Frederick. Okay, so energy estimates you can compute. Okay, it's a similar thing. Okay, so when you see, okay, the thing is an plus 1 is bounded by en under the CFL parameter. This a into delta t by delta x is bounded by 1. Okay, so it's a very clever idea. Okay, because we need okay, the data is coming from the left to right and right to left. Okay, let us give okay the data okay whatever is required for the numerical scheme. Okay, so in the numerical scheme you are feeding the data from left as well as right. Okay, so why can't we change the numerical scheme also a little bit and see the numerical solutions? This scheme will work, but it is more diffusive in the sense, okay, you may not get the okay exact solution accurately. Okay, this we will see again. I'll give you the code and you can run it. Okay, in the afternoon session. Okay, this is same, and you have to use some identities again here again. Okay, yeah, do I have time or shall I? Okay, fine. Okay, it's 12:25, so I can. Okay, yeah, okay, maybe you may take 5 minutes break. Shall I continue? Okay, that's fine. I don't know, it's assembling is another. Okay, 5 minutes, fine. so you will get second order, okay, scheme, okay, obviously here. So now the case is how to replace these derivatives in order to make, okay, this is a second order accurate scheme. So replace all the spatial derivatives by the central differences, okay, there are no more, okay, forward or backward, replace everything by the central derivatives. So I can replace, okay, ux by the first order central derivative, okay, this is going to be, okay, second order central derivatives. Now if I do that, okay, this is going to be our new, okay, update for the solution at n plus 1 level by giving it nth level, okay. This is the second order accurate scheme, okay, and this is, okay, again, okay, energy stable under the, okay, CFL condition, okay, modulus of A into delta T by delta X. So obviously here, okay, we proved everything, okay. So this is again the same story, okay. So energy estimate, okay, so multiply by U and, okay, use the some kind of identities and, okay, multiply by delta X and, okay, use the some kind of a telescoping sums and so on, and summing over J, you will end up with this calculation. Everything is, okay, the calculation is there. So the energy, okay, energy at n plus 1 level is bounded by energy at n level under this CFL condition, A into delta T by delta X, okay. These are about the, okay, numerical schemes. So I am not going beyond this, okay, second order. So far what we have discussed: forward time forward space, forward time backward space, forward time center space, Lax-Friedrichs and Lax-Weintraub, okay. So now the question is, okay, one can ask a simple question. There are two more schemes up to this case, okay. So here we replaced, okay, the derivative by the central derivative, second order central derivative. We can replace by the either backward or forward type of derivatives for the second order derivatives. Then in that case there are two new schemes, okay. One is beam warming, the other one is the From schemes, okay. So beam warming is a backward, okay, to the given point J, and From is, okay, using the more number of, okay, data points, okay. So both the schemes, okay, is available. Up to here the numerical schemes, okay. Now let us understand the numerical schemes. Actually this is, okay, a required part, okay. So one is consistency, we have seen. The second one is accuracy, the third one is the CFL criteria. And let us see the convergence in maximum norm, okay. There are norms, okay. So in which norm we have to work out the, okay, energy estimates in general. So we do have, okay, several norms, okay, 1 norm, 2 norm or infinity norm and so on, okay. So the most suitable norms for the, okay, conservation loss is 1 norm mostly we will use, or the maximum norm, but not the L2 norm in general. So because the solutions, okay, come up with the, okay, discontinuities, so it's quite difficult to work out with L2 norms, okay, in general sometimes. So, or in other words, we would like to see the solution structure point by point. If there is any loss in the information, we will always see in the, okay, point to point. Then, okay, it's a L1 norm is most suitable, okay. Even though here you can see, okay, we defined everything here. The scheme is convergent in maximum norm if this, okay, discretized, okay, solution is going to be, okay, continuous solution under the maximum norm when delta T and delta X goes to 0. Okay, if this is 0, then it is a called as a convergent norms. Now we can define 1 norm as well as 2 norm. 1 norm is very basic here, okay. So you know integral over u and, okay, integral over u square, okay. This is 1 norm as well as a 2 norm. Now what we have seen, something new definition. This is a finite time stability or stable scheme, okay. So energy is, okay, kind of a conserve. Let us bring with respect to the norms here. So a numerical scheme is stable, okay. Numerical scheme is stable, okay, providing that, okay, norm of un is bounded by some constant time of norm of u0, okay. So u0 is the initial data. So, okay, whatever the, okay, norm you use, either it's a L1 norm, L2 norm, okay, infinity norm. So norm of un is bounded by some constant time of u0. This ct, okay, it's a constant, is a, okay, depending on certain, okay, condition here, okay. Ct cannot depend on the, okay, delta x. If it is depending on delta x, it's quite difficult, okay, to say it's a, okay, finite time stability. So numerical scheme is stable if for each time t there exists a constant ct, okay, which is a positive, such that for delta x positive and okay, a small delta naught, okay, is a positive, and this delta naught is okay existence in the okay small okay time origin 0 to okay delta naught, okay, where this delta t exists, such that this norm always should hold okay for any given initial condition u naught. Okay, this property has to be satisfied by any numerical scheme for this okay particular linear advection equation or in the conservation laws. And okay, in other words, okay, y to c, okay, this is quite difficult every time. Okay, you can see the u naught, you are starting with the okay initial data and you are going up to the nth level solution and seeing or comparing the energies. Okay, rather than that, can we compare two okay immediate okay level solutions? For example, n to n minus 1 or n plus 1 to n and so on. So the equivalent condition also you can write down as okay norm of un is bounded by 1 plus ct c into delta t times of norm of un minus 1. So you compare two level solution, if they are okay bounded by some constant, then you okay as time is propagating you may not see that okay the energy is keep on increasing. Okay, so it's small. Okay, so yeah, obviously in more okay general conditions, this 1 plus c into delta t you can write down as e to the power of c into some capital T. Okay, obviously it's a exponential term okay expansion, so you can see. And this is okay finite time stability. And the second thing is the scheme is called as the strongly stable. It is independent of constant. Okay, there is no okay finite time stability, it should not depend on, so it's independent of time. Then okay, you can say the scheme is okay simply a strongly stable. Okay, so now okay, so long time run simulations we always depend on okay strongly stable. Okay, why we are saying long time run simulations? So linear advection equation is like a wave propagation. So whatever the okay wave propagation problems, for example ocean modeling and everything, so we always take the data, and data has to be run for the hours, okay, maybe days sometimes. So the solution may come okay at initial at any time level. Okay, for initially okay the solution may look good, after that okay it may spoil or break down, or okay may encounter some okay difficulties. So if you are running in a, okay like computer and okay up to certain time level, for example t is equals to okay 2 seconds or 2 minutes or okay 20 minutes or something, this may not be workable or okay adaptable for the okay real world okay scenario model problem. So for this we need this condition strongly stable, okay, which is independent of any parameter in general. Okay, so yeah, this is you can encounter even with respect to okay, linear advection equation with some kind of higher order okay schemes. When you run for t is equals to okay maybe 2, okay, the scheme looks very really good. And for okay let us say t is equals to 10 seconds itself, then okay the solution structure may lose its okay okay physical significance. So long time run simulation is one of the okay primary criteria for okay numerical simulations of this okay any modeling problems of wave propagation phenomena. Okay, so now let us look at okay as we have seen in the L2 norm, which is the LT energy estimates, let us see in the L1 norm. It's the same structure. So let me explain for one scheme, then you can do for all other. Okay, so now I'll start with the okay again upwind scheme. Okay, I'm not going to say this is a forward time and backward space. So upwind scheme for A is positive. Okay, so now what is the L1 now? Okay, this is the forward time and backward space. Okay, yeah, I think the time is up. Maybe we will discuss in this in the next lecture. Okay, so stability in L1 norm, and okay, what are the problems we will encounter in okay linear advection equation. Okay, and we will see some simulations also in the afternoon lecture. And what is that, how to construct a suitable second order schemes. So what is the difficulties with respect to the okay first order schemes? Okay, we cannot okay capture the smooth extrema. For example, sin pi x is there. Okay, you take sin pi x and get the solution okay for up to t is equals to 2 or t is equal to 3. generally, okay, wherever this curve bends from, okay, upside to the down, you may not get the solution okay, accurately at that point. Okay, this okay, has been studied by the, again, Godunov. Okay, so there is a Godunov barriers theorem, so we cannot construct any linear scheme which is okay, monotone to be a second order accurate. So now we will, okay, see some kind of a, okay, switches how to make first order scheme to be a second order scheme, okay, efficiently by, okay, implanting some kind of a limiters, that we will study. Of course, okay, here Professor Dubey also, okay, okay, proposed some kind of a limiters during his PhD. Yeah, yeah, it's back. Yeah, that we can see some of them. Yeah, that's it.